In this video, we are going to see about ideal transformer with load. In the previous video, that is on chapter 2, we have seen about ideal transformer under no load condition. So here we will see the working of the transformer with load, its phasor diagram, turns ratio, then this dot conversion and impedance transformation. That is how to transform the impedance from one side to the other side. Let us recall what we have seen in the previous video about ideal transformer. We have made some assumptions like there is no winding resistance in the both primary and the secondary coil. There is no leakage flux, meaning that all the flux or the main flux links with both primary coil as well as secondary coil, and there is no core loss, and the core has high permeability. So these are the assumptions made for an ideal transformer. Under no load condition, the transformer draws a small magnetizing current to energize its core. So this current, when it flows through the primary winding N1 number of turns, it produces an MMF. This MMF will create the flux phi in the core. So this flux, which is alternating in nature, links with both the primary coil as well as secondary coil. According to Faraday's law, whenever there is a rate of change of flux, EMF will be induced. So, a EMF E1 will be induced in the primary as well as an EMF E2 will be induced in the secondary. So, these two EMFs will be opposing the cause producing it. That is, according to Lenz's law, E1 and E2 will be in antiphase with V1. Now, this I mu, which is called the magnetizing current, is flowing through the windings which has no resistance, because that is our assumption that the winding does not have any resistance. So I mu lags the voltage by 90 degree because it is purely inductive coil. I mu and flux are in phase. Let us connect the load now at the secondary side. It is represented by Z2 is equal to V2 by I2. So I2 is the current flowing through the secondary winding. So as a current flows through all the N2 turns, you will get a MMF N2 into I2. So this MMF will be such that it opposes the main flux phi. So that is called the demagnetizing effect of the secondary current. So this flux is going to produced by the secondary MMF will be opposing the main flux. So which is linking the E1. So as the E1 tries to reduce, this current, primary current will increase because we know V1 and E1 are equal. So this current will increase to compensate for the demagnetizing effect of the secondary current. So now instead of I mu, the current has become I1, which is equal to I mu plus I2 dash. So previously we saw that I mu is the no load current. Now we need some additional current which will be opposing the effect of the secondary current. So the primary MMF is equal to N1 I1. So I1 I can write it as I mu plus I2 dash. So N1 I1 is equal to N1 into, instead of I1 I can write I mu plus I2 dash. So this is the no load MMF. Now we need this extra MMF to compensate the demagnetizing effect of the secondary MMF. So this one should be equal to secondary MMF. So this part should be equal to secondary MMF N2 into I2. So from this we will get the relation I2 dash is equal to N2 by N1 into I2. So N2 by N1 is nothing but turns ratio K. So K into I2. So we got the relation I2 dash is equal to K times I2. So you have to remember one thing, always the total flux in the circuit remains same irrespective of whatever load is applied at the secondary. So if the load changes, Correspondingly, the primary will respond and it change its current so that always the total flux remains constant in the circuit. Let us see the phasor diagram under no load condition first. So first, this is the supply voltage and the magnetizing current will be lagging by 90 degree. This current and flux are in phase with each other. Then this V1, voltage V1 and E1 will be in antiphase with each other. And the magnitude of E2 can be here or here depending upon whether it is a step up or step down transformer. Okay, but E1 and E2 will be in phase with each other. So this is under no load condition. Now we will apply the load and see how the phasor diagram changes. So we know when you load it, there is a primary current which changes from I mu to I1. So we have to include this I1 in the phasor diagram. So what is I1? I mu plus I2 dash. For that first we should know what is I2 dash. So I2 dash is nothing but K times I2. But where is I2? So I2 depends upon the load. So if it is a lagging load or leading load, we have to draw the I2. So let us take a lagging load first. So in a lagging load, I2 lags E2. So I can, because our E2 is here, I can draw the I2 somewhere here. It is lagging the voltage by some angle phi. Okay. Now, what is I2 dash? K times I2 and it will be in antiphase with I2 dash. Right. So this I2, if I draw in negative direction, it will become I2 dash and the magnitude of I2 dash depends upon the K, turns ratio K. Now we got I2 dash and I mu. The resultant is I1. So let me draw the parallelogram. So you find the resultant one. This is I1. Okay. So the primary current I1 also lags the voltage by some angle. So this is the phasor diagram for a lagging load. We can draw the phasor diagram for leading load also. In leading load, this I2 will be leading the voltage by some angle. So I2 will be coming here and you can draw the other things similar to this one. Next, we'll see about the turns ratio. So we have seen turns ratio K is equal to N2 by N1. In terms of voltage, it is V2 by V1 that is equal to E2 by E1 because it is the ideal transformer. Now, for a lossless transformer, that is the ideal transformer, the input power is equal to output power, that is V1 I1 equal to V2 I2. So from this, you can get this relation K is equal to N2 by N1, which is nothing but, so you see here V2 by V1 is equal to I1 by I2. So here N2 and V2 are directly related or both are in numerator, whereas here current is inversely related. So we can say currents transform in inverse ratio of the winding turns. Next, we can see how to represent this transformer in an electrical circuit. So we have primary winding, secondary winding. The primary winding is connected to the source V1. So let us draw the primary winding and connect it to the voltage source V1. So here it draws a current of I1. So it is here represented here and this is the voltage across the winding E1. Okay. Now secondary side also you draw the coil and connect the load. So because here a load is connected, here while drawing you can connect the load. Now to represent this core, normally these two lines are represented. So here if it is a air core, you need not draw anything. If it is a iron core, you can represent it like this. And normally it is used to represent the turns ratio because we don't know number of turns in the coil. N1 is to N2 will be represented here. So what is N1? N2 by N1, that is the turns ratio K. So only if we know this one, you can analyze the circuit. So this is an important parameter in a transformer. And the next is, there are two dots here. This is called dot convention. So this is used to indicate the phase relationship between the primary and the secondary winding. So if you have this voltage, it can be positive or negative. But both the windings will have the same polarity if the dots are here. Okay, let us see about this one. So you take this transformer and let us keep the dots for the primary winding here, and for the secondary winding also it is at the top. So in this case, let us draw the voltage waveform VAB. I have marked the terminals VAB and this is CD. This is the sinusoidal voltage. So the voltage is going to be sinusoidal here. So if you see CD, it will also be like this. So in phase. So both AB and CD will be in phase. So if you see this case, one dot is here, another dot I am keeping it here. Okay. So in this case, the waveform will be out of phase. So the VCD waveform should be out of phase. Okay. So there are many things related to dot convention which we can see later. That is whether the current is entering a dot or leaving the dot. Depending upon that, waveforms will change. Next, we will see about impedance transformation. What is that impedance transformation? So I have connected some load in the secondary side. What is the effect of this impedance on the primary side? So that is what we are going to see in impedance transformation. Or while doing some analysis, we want to know what will be the impedance seen by this source. So I am connecting some load here. What will be the net impedance seen by this source? So that is what we are going to find out now.
Using this relation, let us find what is the impedance seen by the source. V1 is equal to, from this relation we will find what is V1. V1 is equal to N1 by N2 into V2. Similarly, what is I1 we can find. Divide these two, so we will get this relation. So we can say Z1 is equal to Z2 by K square. So what we are doing is, this secondary impedance we are going to transfer to the primary side, so that it will be easy for our analysis. So we are going to connect transfer this impedance to the other side. So what we got, the relation we got is Z2 dash is equal to Z2 by K square. So when it comes here, we have to write it here as Z2 by K square, or N1 by N2 the whole square into Z2. Okay. So this can be still simplified to this one. So all these are same circuits. For analysis purpose, we can do this one. So this is called impedance referred to primary side. That is the secondary impedance, you are referring that to the primary side. Similarly, we can do this for voltage and current also. So everything you can transfer from, that is the secondary current can be referred in the primary side also. So we saw that the secondary side impedance we are referring to the primary side. Similarly, if you have a resistance, if you have an impedance here, it can be referred to the secondary side also. So by this relation, Z1 dash is equal to K square into Z1. So this is particularly helpful when we are when we want to match the impedance for maximum power transfer, because we have studied in maximum power transfer theorem that when the source impedance equals the load impedance, it will be maximum power will be transferred. So for such practical circuits, we can use this analysis. Next we will see about the turns ratio. So we got this relation earlier. What we observe here is that, you see, N2 by N1 is equal to V2 by V1. So the voltages are transferred directly in direct ratio. whereas currents are in inverse ratio. Okay, because N2 by N1 is equal to I1 by I2. So they have a follow a inverse ratio. And impedance, we saw impedance will be in direct ratio squared. So we will see Z2 is equal to V2 by I2, that we know. Z1 is V1 by I1. Now let us divide these two, Z2 by Z1. What you will get? V2 by I2 divided by I1 by V1. So what is this? V2 by V1 is nothing but K. Again I1 by I2 is K. So Z2 by Z1 is equal to K square. So that is why we say impedance will be transferred in direct ratio squared. But the power remains the same on the primary side as well as secondary side. It remains the same, and the volt ampere also remains the same. Next, we will solve a small problem to find how to calculate the primary side impedance. So here secondary side impedance is given in this problem. First, we have to find what is the impedance if we move this secondary impedance to the primary side here. For that, let us find the turns ratio. K is equal to N2 by N1. N2 is 75, N1 is 150. So we will get 0.5 as the turns ratio. So Z2, it is given that phi angle of 30 degree. So what is Z2 dash? It is Z2 by K square. So if you solve it, you will get 20, 30 degree. So you can see that the phi angle of 30 degree, this one, when it is transferred here, it becomes 20 ohms when it is seen by the source. So it purely depends upon the number of turns we use here. So let us summarize what we have seen. For ideal transformer with load, the transformer draws a secondary current. When it is connected to load, it will draw a secondary current which will create a MMF, and that produces a flux which opposes the main flux. To compensate this demagnetizing effect, the primary will draw some more current, and the total flux at any time remains constant independent of the load. And if you see about the impedance transformation, you can transform the impedance from one side to the other side for analysis purpose. So in case of impedance transfer to primary, Z2 is given by Z2 dash is equal to Z2 by K square, where K is the turns ratio given by this one. So and you have to remember that the voltage are directly related, whereas currents are inversely related, and impedance in direct ratio squared, and power remains the same and volt ampere remains the same. If you like the video, do subscribe to Read Electric Vehicle channel. Thank you.